So, in this section, we are going to continue our discussion of different techniques for evaluating integrals. In this particular section, we're going to talk about integrals that involve trigonometric functions, but really just integrals of a couple different flavors. You'll see what I mean when we get to the examples, but there's basically just a couple different forms of integrals that we're going to look at here. And to be fair, it's going to seem extremely arbitrary and contrived, but this section here is basically just preparation for the next section called trigonometric substitution, which I think is going to be much more interesting. So bear with me. We'll get through it. Basically, this is just going to be some practice with playing around with trig identities. And like I said, it'll be preparation for the next section, which I think is a lot more interesting. So I have listed some trig identities here. These are ones which I know I have found some use for in this course. Of course, there are way more identities than this. So if you go to this website right here, or you just do a Google search for Paul's Online Math Notes, Trig cheat sheet, then there's a great PDF that he has written, which has all of the trig information on it that you could possibly need. He also has a sheet called Common Derivatives and Integrals, which I feel like you should have on hand. Because that way, you'll have all of the common derivatives and integrals on hand every time you need them, and you don't have to go searching through all of your notes, or all of my notes, for that formula that you want or that you need. But, just for reference, I have listed a bunch of them here. These are all of the integrals involving trig functions which we have seen so far, including a couple new ones. So the integral for secant is this dude. We never actually proved that. Same here. I think we figured out the integral for tangent in the section on logarithms. Anyway, so you have these here for reference. Also, we can use integration by parts to derive these formulas here. I'm not going to go through it, but these formulas can be very useful. So if you're taking the integral of sine to some power, this formula will give you sine to that power minus 2. So if you had like sine to the power 6, run it through this to get sine to the power 4, run it through again to get sine squared, run it through again, and then you're done, right? Same deal with cosine here. So we may as well start with just an example of using one of these reduction formulas, because these are very, very useful. Incidentally, I would give you this on an exam, if we ever do an exam in person, because I don't expect you to actually memorize this. I mean, I certainly haven't memorized it, but I know that it exists, and that means I can look it up. So let's see, we got cosine cubed. So let's use this formula here with n equal to 3. So let's see. So 1 over n, so that's 1 over 3. Cosine to the n minus 1, so that would be 2, x. Sine x. Yeah, so that's just sine x there. Plus n minus 1 over n, so that's 2 over 3. Integral cosine n minus 2. So 3 minus 2, that would just be 1. So there we go. And now the integral of cosine, well, we already know what that is. The integral of cosine is sine. So at this point, we're pretty much done. In fact, let me just do this. Integral of cosine is sine. And there we go. So indeed, these reduction formulas are pretty easy to work with. So here's what I mean when I say that the examples that we're going to look at in this section are sort of contrived. So here we have a power of sine combined with a power of cosine. Now, the reason that we would be interested in integrals like this is because the technique that we're going to be looking at in the next section, trig substitution, which is, I think, a very powerful and more interesting technique, tends to produce integrals that look like this. So we have to have some strategy for evaluating integrals like this before we move on to the next section. So how do we evaluate something like this? Well, let me just jump straight into the strategy because I have it outlined right here. So power of sine combined with or multiplied by a power of cosine. Basically, it all comes down to which of these exponents is odd. So if the power of the cosine is odd, substitute u equals sine x. Okay, well, it's not. If the power of sine is odd, it is. Substitute u equals cosine. Okay, well, let's just go ahead and do that now. So let u equal cosine. And then we go through our standard procedure every time we do a substitution. So du dx is derivative of cosine is minus sine. Consequently, dx is equal to minus 1 over sine du. And so our integral becomes integral sine to the 5th x. Now, cosine has become u, so this is times u squared. There, that's better. Times u squared. And then instead of dx, I'm going to write all of this. Oops. Got to be careful with that minus sign. Okay. So, sine and one of these signs cancel out. We can pull the minus sign out front. So we are left over with sine to the 4th of x u squared du. Now, of course, we are not yet in a position where we can integrate this, because in order to integrate this, we need to have nothing but u's. But we still have this sine x to the 4th power left over. So what can we possibly do to get rid of this? Well, use the identity sine squared equals 1 minus cosine squared. So this is just this identity right here, but we've just solved for sine square. So use this identity to express, use this identity to express the remaining terms entirely in terms of cosine. So I want to take this dude and rewrite it so that it's nothing but cosines, using this identity. So, sine to the power 4, well, that's sine squared squared, right? So this is 1 minus cosine squared squared. Now, why would we want to rewrite this to be in terms of cosines? Well, because I let u equal cosine. So what we have here is 1 minus u squared. And now we are in a position to integrate this, because all I need to do now is FOIL this out and then hit it with the power rule. So foiling this out, we get 1 minus 2u squared plus u to the power 4. And this is still all times u squared. Now I kind of want to bring this minus sign and bring it back in. So how about I do that? I'm also going to take the u squared and distribute that through. So we have minus u squared plus 2u to the fourth minus u to the sixth du. Okay, and now, of course, this is easy to integrate because this is just power rule. So minus it never gets any better. Minus u cubed over 3 plus 2u to the fifth over 5 minus u to the 7 over 7 plus c. And then finally, the last thing to do is to rewrite it in terms of the original variable. So since u is into cosine, we just replace these u's with cosines. So we have minus 1/3 cosine cubed of x plus 2/5 cosine to the fifth of x minus 1/7 cosine to the seventh of x. And there we go. So yeah, it's certainly not immediately obvious how this works, but ultimately it is the result of two things. One, we chose a substitution, so we did a u substitution, and then we used a trig identity to break this dude apart. So after those two steps, u substitution and trig identity, we ended up with something which can easily be attacked by the power rule. That's generally what we're going to do with all integrals of this form. And in order for it to work, well, if the power of the cosine is odd, let u be sine. If the power of the sine is odd, let u be cosine. Well, what if neither of them are odd? What if the powers of both the sine and the cosine are even? Well, then we can use these identities here. So cosine squared can be broken down into a cosine 2 theta. Sine squared can also be broken down into a cosine 2 theta. Incidentally, these two formulas I think are worth remembering, especially as you progress in your scientific career, because these are formulas that get used extensively in physics, especially when you start talking about waves and things like that. For some reason, that sticks out in my memory. Not much else about college physics does. I just remember using this identity a lot. In any case, here we have the integral of sine squared. So, indeed, we can go ahead and plug this identity right in and see what happens. Alternately, we could use this power reduction formula, and that would also work. But let's use this identity. So this becomes, instead of sine squared, it is 1/2 1 minus cosine. So that 1/2 is a constant, so I can just pull that out. I don't really like the convention of not putting parentheses here. The book does it. I don't really like it. I prefer to put parentheses there. I feel like that's easier to look at. Well, I don't know. It might be more cluttered, but it's less ambiguous, put it that way. Yeah, so now this is easy, because antiderivative of 1 is x, antiderivative of cosine 2x is 1/2 sine. So remember, the presence of this 2 means that you have to pull out a factor of 1/2. So antiderivative of x is 1, or I'm sorry, other way around. Minus 1/2 sine 2x, and this is going to be evaluated between 0 and pi. So let's see. If we plug in 0, we get 0 minus 1/2 sine 0. Sine of 0 is 0, so that all disappears. If we plug in pi, what am I doing? If we plug in pi, we get 1/2 sine of 2 pi. Well, sine of 2 pi is also 0, so this whole term disappears. So we are left over with just pi over 2. So that's it, right? Pi times 1/2. So this identity cleaned this up really easily. And we can do the same thing with sine to the power 4. Again, we can use this reduction formula if you want, but just for the sake of practice, let's use this formula instead, because sine to the power 4 is sine squared squared. So here we have this squared, right? So let's see, 1/2 squared is 1/4, so let that just hang out. Oh, whoops, this should be an x, not a theta. Now, let's FOIL this out. So this becomes 1 minus 2 cosine 2x plus cosine squared 2x. So this is easy. This becomes 1. This becomes 1/2 sine. But we have a cosine squared here. So how do we deal with the cosine squared? Well, in exactly the same way, because we have an identity for that as well. So before moving on, let's go ahead and plug in that identity. And just to save time, I'm going to go ahead and take this 1/2 and distribute it. Like so. Okay, now we can clean this up a little bit. Let's just combine like terms. So 1 plus 1/2 is 3/2. Minus 2 cosine 2x's plus 1/2 cosine 2x's. So what's minus 2 plus 1/2? That's minus 1.5, so that's minus 3/2. And hey, what do you know? I've got a 3/2 that I can factor out. So let's go ahead and do that. So what's 3/2 times 1/4? That would be 2 times 4 is 8. So 3/8. And this becomes a 1, and this goes away. Okay? And now we antidifferentiate. So antiderivative of 1 is x. Antiderivative of this guy is 1/2 sine 2x. And then finally, as one last step, we can take that 3/8 and distribute it. So 3x over 8 minus 3 over 16 sine 2x. That last bit doesn't really count, but or it doesn't really matter, but whatever. Okay, I made a mistake. Sorry, I made a mistake. I knew something felt fishy. So over here, okay, look. So over here, when I'm using this formula, it goes from theta to 2 theta, right? So, okay. So that's fine, that's fine, that's fine. It's over here. So over here, when I use the double angle identity again, this has to go from 2x to 4x. So that was my mistake. Which means all of this is invalidated. Okie dokie. So let me just edit the answer into this so I don't waste any more time. Okay, sorry about that. So yeah, be really careful when you're using that double angle identity, because the angle has to double every time. That's sort of the point. Okay, so So we have seen that we have a strategy for evaluating power of sine, power of cosine. Well, by the same token, we can obtain a strategy for power of tangent, power of secant. And it works in almost exactly the same way. You substitute u equals tangent or u equals secant, and then you use one of the Pythagorean identities to rewrite the rest of the integrand. So if the power of secant is even, substitute u equals tangent. If the power of tangent is odd, substitute u equals secant. Okay, well, what if neither of these are true? Well, that's sort of a strange case. There's no obvious way of going about solving it in that case. And that's one way that it is different from this. Like, you could try integration by parts, but there's not like a single general strategy for attacking it in that case. Thankfully, though, in the examples you're likely to see, that's not going to happen. Well, maybe. So, tan to the 6, secant to the 4. So if the power of secant is even, sure is, substitute u equals tangent to x. Okay, so let's do that. Then, so the derivative of tangent is secant squared. This means that dx is going to equal 1 over secant squared du, which means that our integral is going to be tan to the power 6. Okay, so that's u to the power 6. Times secant to the 4th, x. And then instead of dx, we have this. Okay, so 2 of the secants are going to cancel out. But we are not in a position to integrate yet because we still have x's. We need to get rid of those x's somehow. So next, use the identity secant squared is equal to 1 plus tangent squared. Yeah, so that is the next step. So secant squared becomes 1 plus tangent squared. And that's good because tangent is u. So now we have obtained an integral which is entirely in terms of u. And then from this point on, it should be easy. Distribute the u to the power 6. And then hit it with the power rule. So u to the 7 over 7 plus u to the 9 over 9. And then finally, u is equal to tangent. So we have 1/7 tangent to the 7 plus 1/9 tangent to the 9. And then we are done. So very similar to the case with power of sine and power of cosine. You know, the only difference being we used another one of the Pythagorean identities. So here's another example of that. Tangent to the 5, secant to the 7. So let's see. If power of tangent is even, nope. Or I'm sorry, if power of secant is even. If power of tangent is odd, yes. So substitute u equals secant. So where does that get us? So the derivative of secant is secant tangent. So from that, we obtain dx is equal to 1 over secant tangent du, from which the integral becomes, so let's see, tangent to the 5th Oh, and apparently we're dealing with thetas now. I've already called it x. There. Not like it makes a difference. So tangent to the power 5, secant to the power 7. So secant is now u, so we have u to the 7. U to the 7, and then instead of dx, I'm going to write all of this. Except, we have a secant here. Well, we already know that secant is being called u, so let's go ahead and put a u down there as well. So, one of these u's cancels, one of these tangents cancels. So we have tangent to the 4x, u to the power 6 du. So now we got to get rid of these remaining x's, so we're going to use a trig identity. So we use the identity tan square is equal to secant square minus 1. Well, we don't have tan square, we have tan to the power 4, but that's fine because tan to the 4th power is just tan square square. So we have that. And then this is convenient for us because secant is u. So we have obtained an integral which is entirely in terms of u. So now all we need to do is FOIL that out and then hit it with the power rule. So let's see, that becomes u to the 4th minus 2u squared plus 1 times u to the 6. So if we take that u to the 6 and distribute it through, we obtain, u to the 10 minus 2u to the 8 plus u to the 6. Then hit it with the power rule. So u to the 11 over 11 minus 2u to the 9 over 9 plus u to the 7 over 7. And then finally, just replace the u with secant. So yeah, not terribly interesting. We're pretty much just stepping through the steps of the procedure. But like I said, this is more or less preparation for the next section, which I think at least is a little bit more interesting. But of course, that's going to be a matter of taste. Okay, so here we have a lone tangent cubed. So, earlier on, so if you have just a trigonometric function which is raised to a power, well, for sine, we have this reduction formula. For cosine, we have this reduction formula. So there's that. Or, if the powers are even, as was the case here, you could use one of these double angle formulas for sines and cosines. Here, though, we have a tangent. Now, although a power reducing formula for the tangent does exist, you can find one in the book, it's in one of the exercises, we can actually do this using the same strategy as up here. So we can think of this as tangent to the power 3, secant to the power 0. In any case, if the power of the tangent is odd, then you proceed. Well, indeed, the power of the tangent is odd, so let's just proceed with the rest of this procedure, and it will actually work, even though there's no secant. I think. I hope. Is that what we do? Yeah. We can do that. Okay. So let u equal secant. So I will spare you the details. So as before, we get dx is equal to all of that.